of Malaysia Board of Technologies MBOT Malaysia. Dr. Azrami was the recipient of the Best Student Paper Award presented at the 5th Laboratory Antennas and Propagations Conference, LAPC 2009. He is also the recipient of the Scce University Publication Award in 2011 and also a recipient of the Best Paper and Excellent Awards from IEEE AP/MTT/EMC Malaysia Joint Chapter in 2018 and 2019 respectively. So he is not just a good speaker, but he also a very good writer. So without further ado, I'm not going to put this on hold. Let's get it started. Please welcome our presenter today, Associate Professor Dr. Azrami Abdul Hadi, to deliver his speech. Please welcome, Prof.
Okay, Assalamualaikum and very good afternoon, everyone. I really hope that you can hear my voice. Is everything okay? Can I hear some comment at the chat box? Okay, thanks. All right, thanks. Ada echo sikit I think I should mute this StreamYard, I think. This one. Okay, all right. Okay, all right, so thanks. Okay, thanks. All right, okay. Yeah, first of all, I would like to thank the research committee of the from the School of Computer and Communication Engineering. They have been working so hard to find presenters, which I asked them to start to look at expert in many fields, especially in from the school. And then also special thanks to the AP, MTT, EMC Society from IEEE Malaysia Joint Chapter, who is the co-organizer for this talk as well. UNIMAP Student Branch IEEE, and also Advanced Communication Engineering Center of Excellence. So today, this is the title of the my webinar, which is actually I have been working for almost 12 years, which is still considered as new. But I would like to share with you the knowledge and experience that I have. So then everybody, especially those who are doing research in this field, in antennas or in electronics communication, can further use and then apply to their work, for example. Some people wondering what is DSC Tech. A little bit promotion of Finland here. This is a Doctor of Science and Technology. So this is specially awarded to PhD holders from, I would say, from Scandinavian countries, from Sweden as well. I'm not so sure from Norway, but this is kind of the title that have been awarded to those who graduated PhD over there. Okay, so now I'm working in the School of Computer and Communication Engineering and also acting as the Vice Chair for this joint chapter. Okay, before we start, probably if you can go to menti.com with this code 522509, I want to do a bit survey from where you're coming from. Can you see this code 522509? Okay, is it okay? Is it working? I can write here menti.com.
Yes, sir. It's working.
It's okay, eh? 522509. Okay. Okay, thanks. Okay, so waiting for the response. You can include the institution, where you come from, a company or country. Malaysia, okay. None from Korea or Japan. I'm looking forward to that. Okay. UMS, okay, thank you very much. UMS and then UTEM, okay. Okay, majority Unimap, okay. Maybe we can wait for 1 more minute from Mars. Okay, right. Dr. Sai, Dr. Sai Datul,
Ya, saya.
Diorang kata di StreamYard tu tak ada mic lah. I mean tak ada sound. Is it so? BFB.
Oh, sebab Prof tutup suara.
Okay, should I okay, right, thanks. Yeah, okay.
Audio pada StreamYard ke?
Okay, from Kisai, thanks. Okay.
Cuma dia ada echo sikit kat Google Meet.
Thanks, Kisai from Kenya. Thank you very much. University Malaysia Perli, yeah. You miss this S. Perli also. Very strange. Okay. Anyway, from Tokyo as well. Okay. Thanks. Okay, maybe we can wait for another couple of seconds. Masa University. Okay, thanks. Okay, all right. So next one is actually probably to know your research background, area of interest. I've listed down 10 choices, multiple choices. You can select up to 3. I just want to know the whether you are working on antennas or maybe not relevant to antennas at all. So if you can put your background here. Okay. 25% is like the, okay. Okay, well, anyway, not relevant to antennas, only 15%, 14%, and the rest, I think they know a bit about these antennas, at least doing research or, study in this field. Okay. Okay, all right, thanks. Okay, 15% is not in this field, but anyway, so I can skip many slides then. All right, okay, thank you very much. I go back to the presentation. This is a bit of my research biodata. Probably I don't have to explain this. You have it from the slide. So what I would like to probably emphasize here is I have reviewed 78 IEEE journals, only IEEE journals. So basically know a bit here and there why the papers are rejected or accepted easily and things like that. So I have few slides at the end which I would like to share, especially for the student, undergraduate and postgraduate student. Probably there are some tips. So I think it's very interesting and to know and then to stay until the end of this presentation. Okay. This is the presentation outline. A little bit introduction on antennas, communication technologies, and probably from the single antennas to multiple antennas. So why people are doing research, even companies are trying to include more and more antennas in their terminal or in their any kind of terminal, whether it's mobile or whether it's fixed station. And then I would like to share with you also recent research on multiple antennas. I go specifically on multiple antennas. I did browse with the IEEE Explore, and then I narrowed down to only 2019 until 2020. So there are not many papers actually. So people who are researching in this field, I think is very relevant. Industry keep looking forward and towards the ideas from academia and also others, so that they can move forward in this technology. And then issues and challenges, the main focus of this talk. And then some research highlight which my group and also my faculty probably would like to share with you some things that we have done in this field. And then what is the design rule? Based on my experience, what is the design rule to have a good multiple antennas? Is it have to be, it has to be below than -10, which is normal rule of thumb, or do we have to look at some other parameters? So, which is very interesting to know. And then how to get your terminal antenna research published. So this is particularly in the field of antenna. So based on my experience, then probably I will list down all these possibilities for you to get published with your research work, and then some conclusion. Yeah, this is the normal, well, I mean, conventional way of looking at the radio frequency spectrum, where if you look at from the lower frequencies from 30 kilohertz until 30 gigahertz, there are a lot of well, application. For example, if you look from the long wave radio up to FM radio, this is still we call as low band in communication. So if you look at these low band frequencies, the wavelength is quite large. So when you look at large wavelength, it means that it can pass through anything. Okay, so that's why if you look at your FM or AM radio, it uses a low band frequency range, and we have a very well, I mean, has been many technologies use this frequency range. For example, like this 300 megahertz until 3 gigahertz. So this is where the TV, GSM, and then 3G, wireless LAN, 2.4 gigahertz, all are here. So you can really see that your mobile phone or your terminal, your laptop, normally use this frequency range. We also have 3 to 30 gigahertz, which is normally used for satellite broadcasting. For example, like in our Astro use, C-band, which normally people complain about the why when there is a weather is not good and then you cannot receive any signal. But anyway, it's because of the frequency range used for that application. It's not easily to change to other frequencies because these are already occupied. So there are many things that need to be considered with this RF spectrum. A little bit of 5G spectrum I took from Japanese company NTT Docomo. So we are looking towards the 5G, which is going to be out very soon. I don't know, because of this pandemic, maybe a bit late or a bit postponed. But anyway, it's very important to know the frequency band, because normally in a couple of years back, people always like to know what are the 5G frequency spectrum. But now, at least in some countries and at least in Malaysia, we have already identified the possible, or I would say the frequency band for 5G. So these are from different countries, but in general, they're covering this 3.5 gigahertz, 3.7, and then around this 4.5, and then also around this 26 to 28 gigahertz, which is for, well, we consider as millimeter wave band frequency range. Okay, this is actually from MCMC, which I think they have identified these 3 bands, which is 700 megahertz, which is for low band nationwide. So as I told you earlier, if the frequencies goes lower, wavelength is much longer, then it can pass through many things, buildings and things like that. So that is actually what to cover these long range areas. And then we have this 3.5 gigahertz, which is mainly used for mid-band metro area. And then we have this very small cell, which is for which is by using this millimeter wave frequency range. So these are the three most important popular band, which probably, if one want to do research in this field, well, you have to start to think of antennas at this frequency range. But nevertheless, you don't have to avoid or neglect the existing frequency bands, for example, like 3G and 4G, because that has to be there as well. Because sometimes people really focus on these antennas, but they sometimes miss out antennas at other bands. Okay, there was one paper from who is this guy from Singapore? I can't remember now. But anyway, he studied the out of band couplings, and they exist. So you don't have to focus only on your at your frequency band, but out of band also can couple or at least because of the spurious emission from the other bands, it can also affect the performance of your antennas at your specific frequency band. Okay, this is a little bit more focus on the frequency band that has been identified. You have this low band, which is around 3.3 to 3.4.2, and then some bands is actually for fixed satellite services. So they have allocated this 3.3 to 3.4 is actually for 5G indoor, and then others for other usage as well. And this is for millimeter wave range, which is you can have more wider bandwidth, and you can utilize more of the spectrum. You can have more use cases, interesting use cases that probably utilize a lot of bandwidth. So this is probably the best spectrum that you can use. Okay, some technology terms, probably because along the way I do my presentation, there are some terms which is related to millimeter wave. So basically from 17 to 100 gigahertz is where we can consider as millimeter wave. Sometimes people say about this sub 6 gigahertz. So it's basically between 3 to 6 gigahertz. It's like a Wi-Fi frequencies. So well, I mean, a lot of research in this field, in this range nowadays, specifically for small cell hub, for indoor use, and some also used for outdoor base station for medium range. We have this low band, which is below than 800 megahertz for long distance. Beamforming, sometimes used in sub 6 gigahertz or millimeter wave base station. This is actually to focus the radiation pattern from the antennas towards some direction. So you probably can have adaptive or non-adaptive. So you can see which user, the location of the user, and then you can beamform towards that particular direction. And then we have this massive MIMO, which use large number of antenna elements. Many research in the literature, well, they keep not arguing, but see, I mean, how many elements actually you can call as massive. Okay, some people say about hundreds and others, but majority, I think the majority agrees that if you have 64, minimum 64 elements, which is, if you look at the base station, 8 times 8, which is 64, then it can be considered as massive element, number of element already. So the system can be called as massive MIMO, considering both at the base station and also at the mobile station. Okay, sekejap okay, we try to look at this is actually not my phone, but well, Nokia is always in our heart. Some still Finnish blood here. Nokia Lumia 920, if you look at the size, 13 centimeter times 7 centimeter, and with the thickness of 1 centimeter, if you look at the frequency range that we identified earlier from the frequency spectrum, which is 2G, 3G, and then LTE, LTE, 4G. If you look at the equivalent red color denoted with the red color as well, the 900 megahertz with 33 centimeter. So this is wavelength, 33, yeah? And then you look at other frequencies, and when we go higher, so this is all the wavelength. So where on earth actually you want to locate those, well, I mean, antenna in your mobile phone, right? So you have to, probably you have to wind here, and then you have to make, well, any, all kind of possibilities to be managed to put into this small size of terminal. Okay, so there are a lot of miniaturization techniques which finally we can accommodate those size at those kind of low band frequencies into this phone. Okay, so we try to look at the inside of the terminal, for example. Can you imagine how many antennas here? I use the same phone 920 Lumia. Ada kat Malaysia ni, tak tahu, I don't know. But anyway, we try to look at the antennas here. You look at the main cellular main antennas, which is probably or normally located at the top, which well, I mean, this is where they normally locate the antennas at those areas at the top. We have wireless LAN Bluetooth antenna here, which is at 2.4 gigahertz, which is another second antenna. We have this near field communication antenna, which is normally like this wine shape or this meander type antennas here. And then we have this GPS, which is normally located at the corner. Why? Because they want to have this like a easily fed fed into the antenna, so that they can have circular polarized antennas over there. But when the technology evolves, when you look at the 4G, for example, there are need of second antenna, which is operating at the same frequency of the existing antenna. So, for example, if you have one frequencies here at 1.8 gigahertz or 2 gigahertz for UMTS, for example, you need to have another second antenna, which probably you have to locate somewhere which is left for you. For example, like here or like over this space. Okay, all right. So the best location is normally as far as you can go, because there will be no direct coupling between the two antennas. The closer you get, the more will be coupled, the more actually the power radiated to the other antenna, not to the outer space. So which means that is highly coupled, then it will affect the performance, and probably it will not work at all. Because antenna, especially we are looking for 100% antennas, which radiated from the input to the outer space. So the reason why they want to put high band MIMO antenna here is, I think, very straightforward. You want to have the longest, the farthest distance between this location and the main antenna location here. But why low band? If you look here, 900 megahertz is actually very close to this guy. Okay, so this is actually very close. It's like a couple. Okay, so it's actually at this frequency band below than 100. Below 1 gigahertz. The chassis is almost radiating the whole chassis. But there are some locations where there are less current induced on the chassis. So there has been a study on characteristic mode analysis, or CMA in short. So they have found out that if you place your antenna here and then your low band antenna here, is highly more likely more coupled compared to if you locate your antenna closer to this main antenna. So there are many reasons that you have to consider if you want to locate the second antenna, with due to the spec that you have to know, or the location of the first antenna. So it's a very interesting topic actually to look at. We look at these single versus multiple antennas here. For example, like this is very normal or conventional way of communication system. You have a transmitter here, and then you have a receiver. So how actually you want to improve the received signal at the receiving side is very straightforward. You have to increase the power. It's like a radio. You have to increase the volume, or you have to increase the bandwidth. You have allocated 20 megahertz, for example. Now if you want to increase the received signal, you have to increase the bandwidth. It's like you open the door, you have to make it wider, so then more information can come in. But this is not easy actually. If you want to increase the power, for example, it might also affect the other cell, for example, if this is for mobile station. So it will affect the adjacent cell, which will occur the interference, and it will affect the received signal and things like that. So it's not easy to increase the power, and also it's very expensive to increase the bandwidth. If you look at the frequency band that I have explained earlier, it's already congested at those below than 6 gigahertz. So it's very expensive to increase. So one of the easiest way, well, at the expense of a little bit more complex, you don't have to increase the power, you don't have to increase the bandwidth, and then you can easily get the capacity improve like a double of that. I mean, for example, if you look at 10 signal to noise ratio at 10 dB, for example, this is one single element, Scce, single input, single output. You can have something like 3 bit per second per hertz. But if you increase the number of antennas at transmitting and receiving side, so you can have like almost 6 bit per second per hertz. So by adding more antennas, actually you have more doors, you available more bandwidth, so then you can utilize that, and then you can efficiently use that to multiplex all those streams inside there, and then finally you can increase the data rate. So I think that is the goal of having these multiple antennas. Okay, so if you look here, the benefits of multiple antennas, I just want to go through this. I think this is very important to know as well, multiple antennas. Basically, if you have more than single element, you can control the beamforming instead of only one. I don't think you can. I think it's quite difficult to control the radiation pattern with only single element. And then finally, you can increase the receive power. So this is multiple element, but with single port, I would say. Okay, so you can definitely get the increase in gain. But try to consider if you have two receive signal. Okay, signal one, I should have color here. Signal one, as a function of time, antenna one receiving signal one, and then you have antenna two receiving signal two. If these two guys very different or no correlation at all, which means that the signal are totally different, isn't it? So if one guy is moving at this location, I don't know, maybe this is behind the building, next to the building, and from the base station, you cannot see at all the location of the base station. You're moving, and then you probably experience at this deep fade there. But if you have second antenna, which is totally different from the first one, so you can have a signal which is a little bit different, or maybe 100% different. So if you have some other combining techniques, there are a lot of techniques like maximum ratio combining techniques and others. So if you combine with that, you can actually mitigate the multipath fading. Okay, so you can always have a best signal according to the signal. Combined technique that you use. There are multiple techniques. Then you can always have a peak, which is always good. All right. So this is one of the ways to mitigate multipath fading. All right. So I'm looking at this CMO. I'm saying about CMO, which is single input, multiple output, or in this case, only two antennas at the output. So what happens if we have multiple antennas at the transmitting side as well? Okay. I forgot to say this number two, you actually transmitting the same signal. I mean, the same signal, I mean, you have a bit stream, for example, 010101. So you send the same signal. So if you are receiving two, then you can actually mitigate the fading over there. But from this point, it's actually you can you can chop it into two, and then you can send it to the other side, which is at the receiving side. And then from here, provided that you know how the channel looks like, you have to study the channel as well. So at this point, at this receiving side, you are receiving signal from this guy, also from this guy, and then at the antenna two, at the receiver from the first transmitting and second transmitting, and then with proper deconvolution techniques and others, so that you can easily reconstruct again the received signal. Okay, so by doing this, you are actually multiplying or you will get the higher data rates. So provided that the channel or the information of this environment here is spatially orthogonal, which means that is very rich multipath inside there. So this is the benefits of multiple antennas. Okay. All right. So this is some of the example which when I started my PhD, I tried to explore how the multiple antennas looks like. So for example, like this is group from Germany. 3 IFAs there, and then we have one from Yahya Ramatsami group from United States. They have using this 4-port, and then this is actually my antenna, simple 5 IFAs. We use this as a radio direction finding, which one of the Nokia project over there last time. And then we have this. This is also in one of my ex-colleague from Germany as well. And then some others, which is multiple ports. So we are saying here, multiple antennas with different ports, I mean, with separate ports. Not like an array, normal array, which only single port, and you have a feeding network to multiple antennas, okay? All right, so feature need, I don't think I have to explain this. Is obviously for you to increase the data rate, you want to use inside your smart home and the smart services. So the best, if you ask me, then probably you have to have these multiple antennas to accommodate your wish here. For 5G and Internet of Things, this is always the need of the future. What I would like to share here is the 6G. This is very good, where recently published in IEEE network here from Walid Saad, can't remember which university, Virginia Tech, Mehdi from Oulu University, Finland, Ming Chen from, I don't know, from Beijing. So it's a, international collaborated paper here. So if you look here, the driving application for 6G, for example, multi-sensory extended reality application. So they're looking at extended reality, not virtual reality like you look at virtual now, but in a sense that you are connecting to other intelligence into your system. So if you look here, driving application number 2, connected robotics and autonomous system. So you have, I would say 6G, there are a few intelligent systems which need to be collaborated all together. Okay, so this definitely needs more bits, spectrum, obviously in millimeter wave, massive availability of data, and then others. So these are technologies which we believe that can support or to enable this 6G. Obviously, we have to use this millimeter wave. We can have more bandwidth. Edge, AI, artificial intelligence, and others, which is, I think, probably this is too futuristic, but I think it's important for you to know, and then in future, this is how it move forward. Okay. All right. Recent research on multiple antennas. I will go very fast here. This is very short example. This is 8 element from a group from Korea, I think. It looks very complicated. And then this one for 3.5 gigahertz multiple antennas. This is also 8 element. They use this, what I mentioned earlier, characteristic mode theory to locate the location of the antennas. And then we have also 8-port antennas with different user effect, which you always have to study if you're working for terminal antennas. Okay. And then we have this also, this ultra wideband. If you look at the frequency band here from 3 to 6 gigahertz, so I think it's very promising prototype. And then we have also this 10 element, some example of dual band antennas. So, if you look at the frequency band here, it's actually quite easy to get lambda by 2 distance, I mean separation. So maybe they just want to see how this 10 element or 8 element perform in this compact size terminal. All right, so this is a 12 port. They also look at the integration with battery and screen as well. I think this is also important to include in your simulation, not only like only chassis. So if you can include this, also very interesting to look at. All right, so this is one of the performance metrics that I explained earlier, this correlation, which normally they targeted to get below than 0.5. So if it's less than 0.5, which is actually 50% or 3 dB correlation, I think it can be considered good for MIMO application. Okay, some example for laptop. So you have 4-element laptop, 4-element MIMO antenna here for 5G laptops. This is also working at 3.5 and around 5 gigahertz. Some example of 28 port. This is MIMO cube. If you look here, it's a cube which is used for indoor micro base station. So also very interesting to look at. They study at the look at the throughput as a function of this space. And then you can clearly see that probably this is very where high throughput can be obtained at this azimuthal plane. Okay, example of indoor base station. Okay, yeah, okay, all right. So this is a very interesting paper, which I think this is the first experimental paper on millimeter wave on terminal antennas. So this Professor Won Bin Hong. He's now in Korea. Has been working with Samsung for I think 15 years. Very experienced researcher. He studied this how this normal planar millimeter wave antenna behave or operates when it's on terminal side. So if you look here, well, I mean, I would say the main lobe radiation is still going to the same direction, but due to the presence of all these other components, you can clearly see the side lobes are probably getting a bit not really focused anymore. So that probably will give you effect. But nevertheless, due to that, if you look at the maximum gain, is reduced a bit, right? Like 1 to 2 dB. Obviously, if you have user hand here, it will definitely affect like 4 dB compared to without user hand. All right, so he also studied this this array, millimeter wave array at this location, at the other location as well. So by doing this, they can beamform or beam steer the radiation pattern. This is like the conventional antenna phone, which all the antennas here. So he tried to also to locate the millimeter wave array at some other area here, I think, and inclusion of the radio. So I think it becomes more complex, structure now. Okay, so he also has fabricated and tested with different kind of user effect. And if you look at the measurement setup here, is very complicated. I don't know in Malaysia we have this setup already. So, but anyway, we are very much looking forward if industry want to donate, okay, or want to set up. Then we are very much looking forward to collaborate then. All right. So, but it's very interesting research field as technology evolve. Then I think obviously in future we will try to cope with this millimeter wave terminals. All right, so some figures as well. Millimeter wave antennas, they still have this LTE 1, 2 or sub-6 gigahertz antenna. So you still have to have these antennas on board. So one have to consider as well while designing other futuristic or future antennas in your terminal. All right, for example, like this, they share the antennas like a 3.5 and 28 gigahertz here. So they have 3.5 is actually the larger one, which is the dipole type, and then we have this 28 gigahertz, this one. And if you look here, this is the test board. Test board looks more complicated than this guy, you know. So for millimeter wave, I think is very costly research, very high cost research. Some other photos from this guy also. Array antennas, array 1 and array 2, working at around 26 to 28 gigahertz. Okay, and then the next paper, go very fast one. This is like three areas with 8 arrays, so they can actually beamform or switch the pattern to which area that they want. So it looks quite promising from this group. Okay. All right. So issues and challenges. So those are the research that researcher has been doing for quite well for the last 2 years, and I would say that the it is very promising field. And also when I browse through this IEEE Explore, is only up to 50 papers or 40 papers only on millimeter wave terminal antenna. So of course, cost is one thing, but definitely this is the way forward if you want to do research in this field. Okay, so issues and challenges. I just want to go through very fast. We definitely want to include more radios, but given the space is very limited, how we want to include more radios inside there? So we actually have to share the antennas in future, I would say. Okay, even though people say that the more radios, but the size become probably thinner, or I don't know, but one has to consider that as well. For the antenna engineers, they don't have much space to do. They only given that space in order for design, to design multiple band antennas over there. Okay, so you also have to consider low frequency systems such as FM and AM radio, which requires, well, quite a bit larger antenna compared to others because of the low frequency band. Okay, and then how to implement antenna diversity and MIMO in that terminal. Everything into one terminal, which is very, very tedious job to locate or to place your antennas. For example, like mutual coupling, this is one of the things which is very important to note at. If you have different antennas, either it's working in the same band or out of band, different band, there still exists coupling. And if you consider the mobile PCB circuitry, they're also coupling between the components there, which obviously can deteriorate or affect the operational frequency. The bandwidth is not as expected. The radiation pattern, for example, is being tilted to the other direction. So I think it's not easy to handle this. Perhaps, or furthermore, if you hold the antennas and then with this coupling already exists without user hand, so there exists absorption loss. So imagine if you have without hand or single antenna element only 50% efficiency. So if you have this, it's like you will kill off your terminal performance. And that is what has been happened to the iPhone 4, for example, last time, which they have this metal frame antennas, like the whole, they cover this, this round around the chassis, which when user hold that, and then it becomes, the performance become bad. Okay. So, and then if you look at the environment, for example, this is also very dynamic. This is the case where it's not moving, but if moving, then there are reflection and then shadowing from the trees and the diffraction and things like that. This will probably affect the performance of the terminal. Okay, I would like to show some slide also. This is with one of my students working with user effect, for example. So we look at what kind of parameters that has been affected due to the user hand. So there are a lot of mitigation techniques here, antenna shielding or whatsoever, but everything comes with complexity. Okay, for example, if you want to get to improve the efficiency by using this technique, is still considered less. But if you want to have more switching and others, switching, probably you can switch to good antenna, but then you switch, you include more complex in RF circuitry. You also include losses in the circuitry, so that also you have to compensate when designing the whole terminal. Okay, and then imagine millimeter wave, very small antennas, even though it's array very small, and then you cover with the hand. I don't know whether, well, most probably it will be deteriorated with the user hand. For example, if you look here in the talking mode and data mode, the CDF curve of the capacity has been shifted to the right, so you can see the less affected by the user hand. Okay, and then future terminals. I mentioned earlier the issues and challenges, but for future terminal, you don't really know how the terminal looks like. This guy, this guy, I mean, holding this strangely. I mean, this might be one of the way that people hold the terminal in the future. Or your phone actually become a Tetris like this, or just a matter of in a phone, sorry, the pen type of terminal, or it can be very flexible, like what Nokia Morph 2008 has introduced this concept, but until now it's 12 years already, not yet, and Nokia probably not so popular anymore. But this is from their Cambridge lab. They have used this nanotechnology to have this well, I mean, like a flexible substrate, and then try to have this, but I don't know then how it goes. But this was one of the concept that has been introduced by the Nokia at that time. Okay, so some research highlights, maybe very fast one. Okay, we try to look at the coupling at low band, which is below than 1 gigahertz. This is for two-port network, two-port antennas. We try to use simple antennas like PFA antennas, because we don't want to complicate ourselves. If we have a very complicated structure that we don't understand at all what the antenna looks like, or how it behaves, or how it should behave. So we started with PFA antennas. And then if you look here, the coupling, if you look at the green, the orange color here, the coupling is like -3 dB, which is 50% is actually coupled to the other antennas, which you don't want. You pump that signal, but only 50% radiated. 50%, another 50% is actually coupled to the other antenna. Okay, so we try to have this decoupling network with a very simple circuitry, and then we able to decouple them. And if you look at the S21 is actually the coupling between the two, behaving the same as S11. Okay, so this is actually what the decoupling should behave, the decouple, and then both antennas can work perfectly like what it should do. Okay, so if you look at the on the right side, we have this efficiency, which actually improve with and without. It improve a bit, but we are trying to look at why the correlation a bit becomes worse, become worse compared to without. So we try to still to look at this, but nevertheless, it's still below than 0.5, which is 50 dB, 3 dB. So it's still considered good. All right, this has been reviewed. Under review, we plan to resubmit this paper, and this is MCO punya paper lah. Okay, while MCO we managed to submit this, review and submit this. Okay. We have another one. Dr. Rizwan now working in late technologies. Is a two-port antenna network with reduced user effect. Okay, so we try to design antenna with which the user effect can be reduced. So we have the one that we propose is a non-identical elements, is with different feeding network, and then we compare with exactly the same antennas with same port location, with same size. So then we can fairly compare them, and then we look at the efficiencies, and it somehow improve. I mean, for example, like the reduction actually only 28 and 25% when there is a user, compared to 72 or 63% in terms of the multiplexing efficiency when normal or conventional PFA. So it's like quite a good improvement. Well, I mean, if there is a user, always there is a degradation or absorption loss. But we try to look at how we want to reduce that effect. So on antenna design part already, we can try to somehow use or use the concept of that non-identical elements and different feeding networks to create more diversity of that antennas.
Prof, sorry,
So then,
the slide, the main slide is not on the screen. So as you are explaining, it's
this one, this one okay?
I think someone also put down on the chat just now.
I
It
cannot
is
see the chat.
interesting.
Yeah, okay.
You just need to pin. You need to pin the slide to the screen.
Is it okay?
The presentation is still not. We can see you, but not the presentation.
No, we are okay, sir. Yeah, I think they didn't pin your slide to the screen.
Macam mana? Can I continue?
Yeah.
Continue je bos, saya okey sini di JB.
Okay, UTM. Okay, UTM clear. Alright, thank you. Alright, so thanks. We move forward. I have 60 slides, so only 20 more. I think we are at a good shape. Okay. Please stay until end of the session because I have quiz. Okay. Iklan saja. Right. And then this is millimeter wave terminal antennas. Of course, we don't have any facility to fabricate and to measure and things like that, but we still want to do this. We want to have some idea what will happen when we design millimeter wave antennas, and then for at that time we don't know yet this 5G. Well, I mean 28 gigahertz. So we try with this 15, 28, and also 60 gigahertz. We try with different users' hand, for example, the distance and also the location of the index finger. So we can clearly see that there is a, well, I mean, reduction in terms of the efficiency and multiplexing efficiency, matching efficiency, and others. But this one is not really meant to propose a new antenna design with a reduced user effect. No, I mean, for example, like this, when we know the for example, finger distance from antenna, like 1 centimeter, is like a reduction of 40% from without user. So this actually we want to give information to the antenna designers where, okay, probably if you want to locate, if you want to have a good efficiency, good efficient antennas, you have to consider the distance at this range, for example, okay? So if it's close, then probably if you want to reduce this, you have to have some kind of substrate in between, so then you can have a closer gap, so then it can actually, well, I mean, reduce user effect from there. Okay, so this is also has been published in Peer. All right, so I just want to move away from the antenna design because probably afraid others a bit boring. But anyway, in MIMO, for example, it's always important to include the environment as well. Okay, one cannot really, I mean, look at only the scattering parameters or efficiency and others. But in order to calculate or to know the capacity, the diversity gain, and others, you really have to include the radiation, the propagation effect. I mean, for example, this is one work that has been done in Aalto University last time, very much earlier in 2008. They have been doing measurement from, if you look here, measurement route from this point to the other point. This is the this is the transmitting antenna, the base station. This is the mobile station. It's like a ball, spherical array, which actually receive the signal from all direction. Okay, so they have been doing measurement from this point to the other point, where they locate the base station, which is the zigzag antenna here, and they move from this point to the other point. So what they have done actually here, they measure all those direction of arrival and others, all important parameters. They know already what is the receiving antenna gain here, what is the transmitting antenna gain over here, and then they use this de-embedding technique to remove those effects. I mean, for example, by a Scce algorithm, for example, they can remove those antenna effect at the receiving and transmitting side. Okay, so what I did last time is I don't have to measure again. Okay, I don't have to go to that which road Unikatu. I don't have to go and measure again. Even though probably if I go there, it will cost some time and cost and things like that. So by having this technology at that time, well, I mean, after you remove this, you obviously can calculate this channel capacity. But then you can include your own antenna radiation pattern over here. So once you include your any kind of receiver here, probably your own design terminal antennas radiation pattern, just include it here. And then you want to have ideal antennas, for example, even though it's not realistic. I mean, like isotropic antennas as my base station. Okay, then you combine again with the propagation medium which has been known earlier. So then you can really calculate the channel capacity, for example, at this point at every mobile location. So you can really know before you fabricate, for example, using your simulation result of a radiation pattern, you can really know the performance. And then the second note from this thing is that you can actually fairly compare if you design few antennas. For example, you have a prototype A and then prototype B from other student or from other researcher, and you want to compare them. Probably you can go to do measurement, but if you go tomorrow, you want to do measurement for the second prototype, it's probably not the same because the environment changed already. So this is the best way actually if you want to compare the performance with use the real propagation environment. Okay, so I have tested, for example, put hands and then we try to see at different and then we can really see which antennas are good and bad. We can actually rank those antennas. Okay. All right. So this is also another work of Ahmed. We try to look at these 18 port antennas because people say that 8 is not enough, 2 is enough. How about 20 antennas on terminal? Okay. So we try to put until 18 actually. This is operating at 5.2 gigahertz or between 5 to 6 gigahertz. So we try to look at if you look at when you increase the number of antenna elements, at some point, there is not much loss anymore. So, well, probably at some antenna, number of antenna elements, you don't have to have it more. I mean, for example, like in this case, 10 is probably enough. Okay, because if you increase more, they probably a little bit increase, but then at the expense of complexity, that will probably give more headache compared to lesser number of antenna elements. So we submitted this to IEEE Access and managed to publish. And then we also look at the performance of some other antennas again. For example, like this correlation with non-uniform environment, because sometimes some research they also only look at uniform environment, means that the signal coming from all direction, but it's actually not. Okay, because if you move in a indoor like a corridor, for example, it's actually not like radiating in all direction. The wave actually moving like a corridor through corridor as well. So I think it's also important. So it's also important to look at this non-uniform environment such that you can really see the real performance of the antenna. So we vary, for example, like this case. Sorry, any question?
Still having problems looking at your slides. I think I'm not the only one.
Okay, which one? It's not. How about others? My slide is okay?
I think some are able to see, but not others. I'm not sure why. I logged out and came back in. I'm not seeing the slides again. That sounds more complicated than designing.
Sorry, say again. Is okay now? Shall I continue? Okay, all right. So thanks. I think it's okay. Then you can see the recorded, right? I mean, hopefully the recorded link is working well. So anyway, this is the performance of the terminal in non-uniform environments where, well, I mean, the ECC, for example, those correlation actually varies when you have different direction incoming signal. Okay. All right. So we come to almost couple of important things left. Design rule for multiple antennas in mobile terminal. If someone is trying to design multiple antennas, I think this is based on my experience, maybe small or little experience, but I think we should follow, or we should have this in mind, these very important three rules. The first one, try to separate those antennas minimum lambda by 2. If you don't have space, you can make it, or you can place it next to each other, but try to make sure that the orientation is different, such that you can have some kind of diversity in terms of the pattern or the polarization. If you don't have any space anymore, try to reorientate the other antennas. Okay, so this is the first design rule, which minimum lambda by 2, looking at your operational frequency. The second one is to design high efficient antennas before you include user, or if you include other components and others, because you have to have antennas at top rank already before the integration of others. We try to design some antennas which is probably so performance or not so high efficient antennas. So then when there is a chassis and also user, it will totally degrade the whole performance. So I think with nearly 100% efficient antennas in the beginning, I think you can get quite a good antenna design after you consider all those other effects. Okay, and then last but not least, non-identical antenna elements. Okay, so I think this is actually I haven't proved this by theoretical, or like theoretical dipole, for example. Okay, but from my experience, if you have not exactly, totally different antennas next to it, you have kind of more the correlation is already small, or already low. Okay, so obviously people always want to start with similar or identical antenna elements, but if you have some other different antenna element, for example, like the paper that we showed just now with the reduced user effect, so we try to use that, and this one, the port 1 and port 2, the left and right one is actually different antennas with different feeding techniques. So you can really see when there is a user effect, the reduction is not that much compared to identical antenna elements. Okay. All right. Yes. Okay. So this is actually secret recipe lah. Okay? Secret recipe for the multiple antenna design. Okay. I've got this. Probably tips to the postgraduate student how to get your terminal antenna research published. This is based on my experience reviewing the papers, not only my comment, but also other reviewers' comment, which we also can look, can share. Because some people say that they just want to look at envelope correlation and that's it. I think one have to include more parameters, okay, which is related to the environment. For example, the first one I mentioned, more performance metrics. So don't be happy that the ECC or correlation is already low, then you can say your antennas is good. But probably you have to consider other metrics as well. And then you have to consider also different environment parameters. Like this one, if you have 2 or 3 antennas, you want to rank them, it might be perform well in uniform environment, but probably not in non-uniform environment. So I think, antenna designers always want to look at the top, 100% efficient antennas. So it has to behave almost similar to uniform and non-uniform environment. Okay, if you're working with terminal design, probably it is good to have user interaction as well. Try to include hands, to head, for example, and then try not to ignore or remove the existing antenna structures. For example, like 2G, 3G, 4G antennas, the previous antennas. So I think that also has to be included there as well. I've seen many papers nowadays, they easily reject because they normally concentrate on 3.5 gigahertz. So then reviewers say that what happened to other antennas? So this is not realistic and this is not practical. So maybe on that part you can take from literature, but the one that you design is actually the one that you want to highlight more. But please don't avoid or neglect the existing antenna structures. Okay, and then obviously one have to have a table to compare existing structures in the literature. I think this is very important. If you look at research papers nowadays, they always have this table to compare. So please try to include this table of comparison, and then you can really position where your antenna design. Okay, some experience. This is actually my last paper. During my PhD, I think this is a resubmission. I submit in January, I think, or in December 2012. So then I submitted here. So they asked for resubmission of this paper, 8-element antenna array at 3.5 gigahertz. Do you know what was the comment? First, I mean, what frequency band is this 3.5? No technology exists at that time. It was 2012 at that time. And then it's very complex to design this 8-element antenna array. So it got to rejection. I assume that this can be accepted at least because this was my last paper to, already completed the list of publication, but I think this is good paper to wrap up my thesis at that time. So I was a bit like this. I want to go back to Malaysia at that time, but have to do some more work, and then a bit fist pump. Okay, what happened, because this is like a futuristic antennas, but well, I mean, we have enough information at that time because the reasons to reject was not so convincing. Okay, maybe I was a bit angry at that time also. I just want to say bye-bye to this paper because probably it's not realistic to submit anymore. But nevertheless, probably 2 or 3 months after that, I improved only a bit. I just add MIMO channel capacity figure there. I submitted to this Q4 paper, MOTL, Microwave Optical Technology Letters. So now you can clearly see that the citation of this. Okay, I very rarely cite this paper. Self-citation, I don't like that actually. Okay, but it stays on the second of the papers that I published, 94. And recently I've got this citation from MIT, which is from this May 2020 IEEE Antenna and Propagation Magazine. So forget about that review. Okay, so this is actually a very good paper. Even I received an email from my colleague, who was my colleague, now working in Huawei, Finland. He asked me to send this paper because he probably don't have this access to this journal. So I think, now probably the 5G antennas in Huawei, 5G Huawei antennas now probably 8-element, I would say. Okay, and then working at this 3.5. Okay, so thanks to my supervisor, lead supervisor, right? For the ideas, brilliant ideas, but it actually being accepted after a couple of years. Okay. All right. Conclusion. Antenna research has great potential to improve the performance of future radio system. Obviously, we cannot neglect or we cannot avoid this research area. The volume actually decreased by a factor of up to 10. Obviously, the volume for the antenna becomes smaller and smaller, and then probably you don't have any space anymore for antennas. One really have to analyze with propagation data just to make sure that you are living in a realistic world. Design. So then you can really improve the prediction of the future non-existing system. Okay. So as the transceiver technologies develop fast, and then this probably can enable the implementation of future smart antenna structures. Okay. So I think that is the conclusion. It is whether it is a threat or opportunity is actually a threat for mobile terminal designers, because it probably, well, I mean, it may well possible that the number of antennas will be over 10. So how many space that we have to locate those 10? Okay, so they probably have to provide space for the antenna designers, which antenna designers use that as opportunity to have more ideas, more new brilliant ideas in order to locate into that small space. So I think from different point of view, it becomes whether it's threat or becomes opportunity, right? All right, so probably this is my last slide. Also from my supervisor, I think it's still relevant. I think in future there are a lot of multi-system, so we don't have much space anymore. Probably we only have this small space at this end and the other end. So looking at different technologies, you might probably have to have matching circuitry to tune or to use any technologies available on board, and probably you have the 60 gigahertz at this area. So actually, this is what we want to highlight. There is a need of this tunable stuff here in order to utilize the same structure of the antenna, and then we can just tune to any technologies that you want. Okay, so by having this at the other end as well, so you can have these multiple antennas, and then at the same time you can really utilize this MIMO. Okay, I think that's all from me. Thank you very much for this session. I pass back to Dr. Saidatul.
Right, thank you very much, Associate Professor Dr. Azrami, for a very wonderful knowledge with us. So I would like to open Q&A session. Is there any questions from members of the floor?
Assalamualaikum.
Salam.
How? It's great. Very interesting topic. Wow, you presented is very well. Anyway, thank you very much for giving this information. I just wonder one question, because the people talks about the massive MIMO. So you talk about minimum is 64 8x8. So how we want to put in the terminals there, because of there is a lot of antennas there. Can you just highlight how is it?
Yeah. Prof, thanks, Prof Kamal. I think it's not possible to put 64 there. I think that massive part is probably for base station only. I think so.
I know. If base station is okay for me, but
yeah.
got giving the same MIMO, basic MIMO for both sides. So I also wonder how to put all the antennas there. Not enough space.
It's probably not enough space actually to locate, because we have to consider the previous technologies as well. I mean, these 3G, 4G antennas, which require more space there. So if you look at the paper from Prof. Wo Bin Hong, this is actually the first paper. I would like to share again here. Am I presenting now? Can you see my slide?
Yeah, sure.
Okay. Well, I mean, for example, like this, Prof, like this. Well, I mean, there is possibility. Well, I mean, for example, like this, 8 here, and then 4 location, probably 32 already.
Yeah.
We might afraid that there is no more space anymore left to have those.
Maybe 4 millimeter wave, maybe it can, because the antenna is smaller. Maybe, but for 3.5, I don't think so, because of the structure also is big, and they want to put some more antennas.
Exactly.
Okay, so thank you. Very interesting.
Okay, actually, we have studied. If you look at my student Ahmad, he studied until 18 antennas for 5 to 6 gigahertz band. I mean, there is no point to design up to 18. Then only 10 is probably enough. So if we consider at the channel capacity, I mean, for example, so there is kind of upper bound limit for that. So one has to consider, well, when you increase the number of antenna elements, there's actually upper bound, which probably you don't have to put antenna elements anymore. So I think that is also one reason why some design are only up to 8 or up to 12, for example. So I think that's my answer.
Yeah, okay.
Okay.
Because they always talk that 5G
Dr.
is
Azrami.
always more.
Yeah. Thanks,
We
Prof.
All right, no problem. Thank you.
Hi, Prof.
Thank you, Prof.
Mandip here. I would like to ask you, did you consider any metamaterial in your design? That is number one. And did you consider any materials? You develop your own materials and you embed your antenna onto the materials. Thank you.
Okay, thanks, Prof. Mandip. Actually, in my research, we haven't considered any metamaterial, so we develop our own new material. But I think it's very interesting to look at those new materials in order to miniaturize that. There is always possibility to have that to reduce the size and also to reduce the user effect. For example, if you can cover some part of the antennas with that brilliant materials, then it can actually reduce the user effect. So we haven't had any, I personally haven't researched much on that metamaterial. But I mean, we try to look at the other way, which is there any importance to have a lot of antennas then? So that's why we try to increase the number of antenna elements until 18. We try to reduce the user effect with some antenna design. But then we haven't really looked at possibility of integrating new material into that. But it's a good suggestion. Maybe there is one way. Well, I mean, there are one of the things that can be considered to improve the performance. Thanks.
Okay, thank you.
Thanks, Prof. Thanks.
Okay, Dr. Azrami, last question.
Okay, last.
Actually, this question from Unimap FB Live
Okay.
from Mr. Ahmed Al Saman and TNU from Norway.
Oh,
So
okay.
his first question is, how much the maximum bandwidth for the antenna in 5G user if you use, let's say, 28 gigahertz? And the second question is, in the mobile for 5G, is the antenna omnidirectional and the beamforming use only the base station or how?
Okay. That's the question from Norway, Okay.
Yes.
Thanks, thanks. The first question is the bandwidth, Okay. If you look at the bandwidth for 5G for 26 to 28, the bandwidth required for that system is only 2.5 gigahertz bandwidth. So if you look at the antenna design working, I mean, how much they can provide the bandwidth, it depends on the antenna design then. I have shown few examples here, which, for example, like these antennas, right, is working from 24 to 28 gigahertz. If you look at minus 10 dB, but if you look at higher, minus 6 dB, for example, you can get wider bandwidth. So it actually depends on how you design the antennas. It's probably there is always trade-off. If you want to design a wider wideband antennas, you have to look at also at the space and also structure and things like that. So if you look at this paper, there is possibility to have up to 4 gigahertz bandwidth at this frequency range, okay, frequency band. So I think possible with that. And then comes back to the second question, whether it's beamforming at the terminal ataupun di base station, isn't it? So there is one paper actually from this is group from, I don't know, Bradford or from Aalborg University. I can't remember this, but this is like beamforming at the terminal side, the mobile terminal side. So it's not only at the base station. I think at terminal side also possible to have this kind of configuration. Okay.
All right, thank you, Prof. I can see that people start to leaving.
Okay, don't leave yet. Don't leave yet. Okay.
You have a quiz.
Yeah. Actually, I have quiz. I want to do some quiz. I actually have things to pass to you for the top 3 winners. Number 3, you can get my, what is this? My thesis. Red color thesis. Not many in the world have this red color thesis. So the number 3 can get this this book. I can pass to you. Number 2, this is one of my precious book. Broadband planar antennas. This is hardcover, hardcover. Bukan main-main macam ni, baru lagi, macam baru lagi. Okay, this is for the second one. And then the first one, I will give you this modern antenna design book from Thomas Milligan. I have met this guy but forgot to get his signature. But anyway, you can get my signature. This is the book. Okay, alright. So you guys can get this all 3. Later on, I can pass to you. Okay. But I have to on the quiz first, right? Boleh nampak ke?
Okay.
Nampak kan ni?
Nampak.
Okay. Okay, can you guys join myquiz.com with this gain code 299123?
Oh, this is quizzes.
It's quizzes actually. I'm waiting for players to join. No one come in. Ataupun tak nampak ke benda ni? Okay. Thank you coming in. Baru 4 orang, mana lagi? Okay. Thank you very much. Familiar name. Okay, it's a very short game, only 5 questions, multiple choice. Okay. Anyone want to join still? Join myquiz.com and then that number 299123. Okay, only 25 person come in. Shall I wait more? Okay, maybe I can wait 1 more minute. Boleh Dr. Sai?
Boleh.
4.26 lah. Okay. Berapa ramai dalam Google Meet tu? Still coming in. Okay, maybe from Facebook kan ada. Okay, these 3 books. I tengok macam mana kalau boleh I bagi lagi my thesis. I have more copies of this. My thesis and then this this also very good book from Wiley, Ning Chen, Michael Chia, Broadband Planar Antennas. Kalau bukan Unimed, I post lah. Kalau Norway tadi pun nak kena post juga kot. Okay, and then the other book is the Modern Antenna Design. All of these are hard copy. Modern Antenna Design, Thomas Milligan. Okay, we got 54. More coming. Okay, kot Okay, I don't think people come anymore. All right, so we can start now. Oh, cepat betul lah ni. Okay. Okay, only 33 done. We have another 50 more. Sorry, 50%. $50 done. Okay. Okay, Dr. Sai,
Yeah.
I can just stop kan? I think it's almost complete now.
Okay. Boleh announce winner ke?
Okay. I think yes. Should I click apa end game now?
Betul, end game. Tapi kalau dah ada bot tu,
Macam mana? Okay. So I think yeah, we have the winner here. First one is Ridwan. Siapa Ridwan? Boleh tengok siapa Ridwan? Tak nampak ke dia duduk main game ke tu?
Mr. Ridwan.
Mr. Ridwan is the first one. Okay, congratulations. Later you WhatsApp me atau you email me azlami@unimed.edu.my. The second one is sorry. Okay, so Ridwan, later on you email me, and then second one is Jack. Then the show.
Hello, I'm Jack from Belgium.
Okay, okay, thank you.
Tadi macam terputus sikit.
Okay, congratulations. Okay, first one Ridwan, and then second one is the Jack, and then third one is Samir. Okay, I know these two fella lah. Okay, and then Ridwan is congratulations. Thank you very much all. All right, so I think I end this session. I welcome everybody to have a future collaboration with me and with our group, with the school. Probably in the future we can see more often. Okay, it's very strange by seeing this, right? I mean, through webinar. Hopefully in conference or some other platform. Thank you very much. Assalamualaikum, and back to you, Dr. Sedatul.
Thank you, Prof. But before we end our session, just a short reminder for those who not register yet for this SSE Research Knowledge Seminar, you may go to the chat box for the link registrations. And can we have a last group photo session? I hope that everyone can turn on their
Alamak,
webcam.
Itulah semua orang dah pergi dah Okay.
Semua orang sudah pergi dah. Tak apa, yang mana ada lah.
Alright, okay, thanks.
There you are, Sami. I can see you. So you are the winner number 3.
Yeah, thank you so much.
I think Dr. Amina will take the picture. Congratulations. So everyone ready? Okay. Hang on, I will take to change layout. Okay. Okay, ready? 1, 2, 3. Okay.
Okay, thanks. Okay. Thank you, everybody.
Right,
Thanks.
Thank you very much, everyone, for spending time.
Thank you, Dr. Azrami. Thank you, Dr. Sayyid.
Right, thank
you.
you. So with that, we end this session. Assalamualaikum and thank you, everyone.
Thank you, Doctor.
You're welcome.
I think they are leaving now, Sai. Okay.
Starting to leave. Good job.